continue with part 2 of Hayut tutorial. Frequent type forcing.
Yeah, thank you, Frank. Okay, so let's recall what we did last time. So we talked about how we want to view the frequency force. So we had some situation using some normal ultrafilter, and over the limit model M omega, we added the sequence of critical points P, and we showed, or precisely Bobsky and Renoir showed that by adding this omega sequence, we actually get the maximal possible model that we can, which is the intersection of the intermediate iterate. Okay. And then we talked a bit, really, like for a few minutes, about the idea of moving objects from M omega P to V and then back to M omega in order to show that essentially adding the sequence P does not do bad things. Okay, so we talked about not collapsing cardinals, but also about not adding special arrangement trees for sufficiently large cardinals and so on. And in this part, I would like to start talking about scales. So what is a scale? A scale is a PCF object produced by Shelach in order to study the power set of singular cardinals. And it goes like this. I'm going to focus on countable proportionality only, so our generalizations, as you probably know, to anything. Okay. So let lambda be a singular cardinal, countable proportionality, and take lambda n to be a cofinal sequence of regular cardinals. A scale is a sequence of functions, or a function in the product of the lambda n. So each of alpha is a function from omega if alpha of n is a member of lambda n, and it's weakly increasing, meaning that for each alpha less than beta, f alpha is at least on a tail greater or equal than f beta, and it is bounding. So for each element of the product, there is some sufficiently high ordinal alpha such that this element is bounded by f alpha. I'm not assuming that it's strictly increasing, but obviously we can always, using those two assumptions, we can narrow down our index that is strictly increasing. Okay, now let's talk about some specific type of points in this scale. So let's take a scale S, and let's take an ordinal alpha of uncountable proportionality. We say that alpha is good, or maybe flat would be a better name, if there is a cofinal subset of alpha such that on this cofinal set, the f betas are not only weakly increasing in the sense that each one of them is larger than the other on a tail, but you know exactly which tail it is. So there is a fixed n, a natural number n, such that above n, those f alphas are increasing. Okay. Yeah, okay. Just in order to be able to say something like there are club many good points, things like that, we let all ordinal countable proportionality be good. This is, I mean, there are some variations about the definition, right, which I don't care. Okay, so a scale is good if there are club many good points. Now, if we think about how, think about how we can try to construct. So typically when we try to construct a scale, we are going to say, okay, let's define some f alpha by induction, each time trying to make larger and larger. And when we get to a limit point, if it is of countable proportionality, we can typically take some diagonal thing. And if it is of uncountable proportionality, it would be very nice that this point would be good, because then you can take simply the point with supremum of some final subset of the beta so far in order to define our F alpha. Okay, so it's very nice to have a good scale in the sense that it's quite ordered. The scale is not good, it's bad. And let's just note a few easy things about the bad points of the scale. So we denote it by bad of f. And if we have two scales of the same product, then the set of bad points in both scales are essentially the same. The symmetric difference is non-stationary. So the collection of bad points does not really depend on the choice of the scale, it just depends on the choice of the lambda n, up to lambda. Very sketchy proof. The idea is that if you have two scales on the same product, then they are interleaved. Each of alpha, for each of alpha there is some g beta which is above it, and for each g beta there is some f alpha prime which is above it, and so on. And this means that on the club, essentially we will have if we look at the scale of f up to alpha and we look at the scale of g up to alpha, they are already interleaved. Now it's not very difficult to see that once alpha is uncountable to finality, it is a good and it's good for f, then it's going to be good for g, and vice versa by looking and interleaving and maybe narrowing down a bit, shrinking down a bit the witness probability. Okay. Now, a few additional facts. So Cher proved that if there is a scale of length lambda double plus, then there is a good scale. And when I'm saying a good scale, it's always of length lambda plus. There is a good scale on lambda. The trick using is partial square. And in particular, there is always a good scale on the first cardinal in which the singular cardinal property is fair. And it was a question I think raised by Wooden. Is it consistent to have the scale of SCH while having a bad scale? So we know that there is a good scale. Can we have also a bad scale? Obviously on a different product, but of the same cardinal. This question was answered by Gittit and Sharon in Sharon's PhD thesis, I think. They constructed a force in order to get such a model. What I'm going to do in the first part of this talk is to describe this forcing from the iterated root of our point of view, and to see why this point of view gives us the preservation of bias scale in a quite natural way. By the way, in those settings, they can also add into elliptical labs, and I hope to get to this also in this talk, but they can only make the singular cardinal to be alpha omega squared, and for reasons that would be clear once we get there. They couldn't get to lambda equals alpha omega, and this is still open. It's still open whether SCH can fail at alpha omega while there is a bad scale in alpha omega plus 1. Even negation of witness. Okay, so let's talk about the Gittit short. Let's start with a sequence of measures. Each one of them is a kappa, Vn is a kappa plus n super compact measure. And we define an iteration. We first hit V0, which is simply a normal measure on kappa. Then we have some J1, we hit J1 of V1, which is U1. and so on. So at the end point of the iteration, we are going to hit Jn of Vn, which is what? It is a Jn of kappa plus n supercompact measure of in the model and okay. What is going to be our frequency? Okay, so let's deal with them. So the generator for UN is going to be this. The pointwise image of the ultra-power map over the domain of the mesh, right? Because it is a super compact mesh. But we are going to keep iterating after we give this ultra-power. This situation is going to move the object by this map, Jn plus 1 omega. Note that this object is quite small, smaller than the critical point of this map, smaller than the Jn plus 1 map. So it means that it's the same as this, the pointwise image of Jn omega over Jn kappa 1. Okay? So we have a frequency, the sequence of those Pn's, sequence of the generators of the UN, then all the way through to n omega. This is exactly the recipe that we had in the last one. So we already know we would have that m omega of t is the intersection modulated if it's closed under kappa. What else do we know? We know that the union of the Pn is simply going to be J omega of kappa plus omega. Every ordinal in J omega of kappa plus omega comes from somewhere, comes from some sufficiently large n and sufficient so that it is below J omega of kappa plus n, and this ordinal comes from some slightly larger n. So it is going to be covered by Pn. Each one of the PMs is small. This means that in this model, m omega of t will collapse to a cardinal between kappa plus omega and kappa. So let's say J omega. So J omega of kappa plus omega has such J omega of kappa. Oh, we didn't add bounded kappa to J omega of kappa, so we can be singularize it. The new successor is J omega of kappa plus omega plus 1. Every other cardinal is a continuity point, so it's not closed. Okay? Okay. What? Okay, we will not assume that kappa plus omega is strongly in our application, but it's worth noticing that if it is, when J omega of kappa is exactly kappa plus omega, and J omega of kappa plus 1 is kappa plus omega plus 1, so it is kappa plus omega plus 1. This is, even though this is not going to be, this is worth noticing because it means that if you are doing the Dietrich-Sharon forcing over a model of GCH, for example, then you should be able to pull back and forth objects from kappa plus omega plus 1 in m omega of t, which is the successor of j omega of kappa, to a kappa plus omega plus 1 of v and back to n omega. So this means that the Dietrich-Sharon forcing has the same properties of being able to pull back and forth objects between the successor of kappa plus omega, successor of kappa plus omega and v, and the successor of j omega of kappa and m omega t. And this is always what we would like to have in the Dietrich-Sharon set. So we start with a successor of a singular kappa plus omega plus 1, and we end up with this very same cardinal being the successor of previously regular. J omega of kappa. Okay, what else? Okay, so we still have some continuity. If we look at the kappa plus n plus 1, it is a continuity point of Jn. It's not going to be a continuity point of Jn plus 1. If H holds, it's actually yes. Okay, so some notation in order to spare me the need to say again and again and again kappa plus omega, kappa plus omega. So it's too much. Let's call it kappa plus omega lambda and image under J omega lambda omega. And when I'm saying lambda omega plus, I mean the successor in M omega. And when I'm saying lambda plus, it's really the successor of lambda in G, kappa plus omega plus 1. So the usual one. Okay, so let's start asking questions about it. Fix a scale in M omega on the following product of cardinals, Jn of kappa plus n plus 1. Okay, so those cardinals are going to be below J omega of kappa in all. And they are clearly regular. And let's assume that we have such a pair of length lambda omega. And let's say a similar scale over V. Okay. So here is we want to compare something. So we have this scaling V, F, and knowing things about V, we might be able to say that F has a lot of bad points. That it has stationary many bad points of small cardinality. And want to conclude that in M omega of V, G also has a lot of bad points. At least stationary many bad points. Now, how are we going to do it? So, so first of all, even though Jn of kappa plus n plus 1 is not really a regular cardinal in T, we know exactly what the finality of it is. It's a continuity point of Jn, which means that if I want, I can sort of transform the scale into a scale over the product of kappa plus n plus 1, which I call H. So how am I going to do this? I'm just going to take H alpha of n to be the least ordinal that's going to go past G at the point J omega of alpha n. And this is well defined because everything here is continuous. Jn is continuous, J omega is continuous, and M omega of T is closed at a countable sequence. So whenever you want to bound something, we can do it using G. So we have some other scale, H, which is a scale in V over kappa plus n over the product of kappa plus n plus 1. So it should be interleaved there. Note that H might be constant on some intervals, and again, we don't quite care. We can always shrink it to be within P. Okay, take some cloud M omega 3. And we can take this club and pull it to less than kappa closed set in V by just asking which ordinals are going to go to this club, which ordinals alpha are going to be sent by J omega to this club D. And we can shrink it and make H to be strictly increasing on this less than kappa closed. Okay, great. So F and H are interleaved, which means that the cells essentially have the same bad points in the class. So H should have plenty of bad points alpha such that alpha Fibonacci is sync up. Now, what are we going to do? We essentially going to, I'm sketching this part a bit, but it's quite straightforward. So we are going to compare H and G, and we know that if alpha is a bad point for H, so it should be a bad point for H as well. But J omega of alpha is a good point for G, and we can assume that alpha has cardinality below the critical point of J omega. When we can now start asking questions about how G looks on the image of J omega D prime intersection alpha. And this sort of sequence of elements of the scale G by itself, in some sense, interrelated with H in the sense that we had before, setting each element of H, the nth element of H beta under Jn. Okay, and this means that by taking a witness for a goodness for G, we just get a witness for a goodness for H at the same ordinary. So I'm slightly rushing this, but it should be possible to complete the detail. The point is that let me say, since m omega of t is closed under countable sequences, scales in m omega of t make sense. There are almost scales in t. The only point which is missing is that they might not be on cardinal, right? On a real regular cardinal. They might do something else, but we can always take such a fake scale and make it a real scale, and then we can do some analysis in V, comparing those scales to what we have in V, and get some consequences like if V all scales are bad, then this scale cannot be too good. Okay, so let's now derive the Dietrich-Sharon theorem. So the theorem is that it is consistent relative to a supercompact cardinal. SH fails at some cardinal kappa, which is singular, strong, linear cardinal, countable for finality, and kappa carries or kappa plus and carries a bad scale, and an inconsistent but which cardinal can set that. So how are we going to do that? Start with supercompact cardinal. So above it, there are no scales of length larger than the successor of the singular, and all scales are bad. Oh, shoot, it's a power. Okay, first to make 2 to the kappa large, let's say above kappa plus omega plus t. And look at the Dietrich-Sharon model, M omega. Now, in this model, what happened? In this model, kappa omega is going to be quite large, right? It's way above J of kappa, but we didn't need to know that. And it is a singular and strong limit cardinal. And the power set of it is strictly larger than the image of kappa plus omega plus 2 as the second omega is redundant. And so we have a failure of SPH with this cardinal. We don't collapse cardinals outside the interval between kappa omega and lambda. And last thing, we know that there is a scale on Jn of kappa plus n plus 1. We know that it has to have the right length because we can put it to a scale in V, and all scales in V have the right length, and we know that it has to be bad. That's question. Should I go slower? Okay. So next, Let's talk about violating SCH. Okay, so we already violated SCH, right? But let's talk about violating SCH without violating GCH below our cardinal. So, okay, this is the goal. We want to get a singular strongly cardinal kappa, such as 2 to the kappa, strictly larger than kappa plus 1, but we don't want any cardinal below it to violate GCH. Okay, so we don't want to do some preparation and enlarging the continuum of many cardinals below a measurable cardinal, then we're pretty important. We don't want that. We want to get the least fail of the GCH to be a strong singular cardinal. And the fourth thing doing that is the standard-based principle. Now, what I would like to do now is to sort of try to convince you that we can get the standard-based reporting, at least the version of Tavim Limovich, just it's going to arise naturally from this perspective of iterated root of power. So let's do it. In order to get 2 to the kappa to be large, we want kappa to the omega to be large. We want to add many omega sequences to our cardinal kappa. Okay. So we are going to have some iteration. I'm going to say in a moment what it's going to be. And I'm going to add for each ordinal below some j omega of lambda, a sequence extension, some PR, some cofinal sequence in R. We want all the post-Kidon properties to hold. We want m omega of p to be in some sense controlled by the iterate. And we are going to have problems with that, but let's see why. So first of all, we want to have an elementary embedding. The elementary embedding cannot be just elementary embedding using normal ultrafilter. We need slightly more. And the definition, you two is of a tall cardinal. So a cardinal kappa is lambda tall if there is an elementary embedding P from J from P to M, such that M is closer kappa sequences in order to make this definition non-trivial, and J of kappa is at least lambda. Okay. Now, there is a combinatorial definition to the same concept, but we don't really need it. So we can code this elementary embedding by some sequence of measured kappa split ultrafilters on the kappa. The only thing that we would need from this path is some notion of width of the embedding that I'm going to talk about in a minute. But let's assume that we have such a combinatorial object called extender that we can derive the tallness embedding. And we, again, are doing an integration. We start with V, we take the outer power, we move the extender, again and again, we take the direct limit, it's going to be well-founded, and what is going to be our P? Okay. So for each, there is a mismatch of alpha and gamma. So for each gamma below the eventual length of the extender, we would like to get a frequency. But there is a problem here. If you take such a lambda, well, it is going to be generated at some step of the iteration, at the nth step, and from this point we can actually, so we have a well-defined sequence starting from there. It's the images of this, starting with this alpha, and we take the images of it under the embedding. This is P gamma, but we don't quite know where to start. So the sequence is actually defined up to a finite shift. Okay, if we especially know that we want it to be definable inside of the MN, and the MN cannot really know if an ordinal was originated in it or in the previous steps, because MN does not know anything about the previous step. So, for example, the sequence of ordinals that comes from unity is not a member of M1. If it was a member of M1, then we would have a supercompact embedding. So we don't quite know where to start those P gamma. And okay, so let's define an equivalence relation. Okay, so let's say the two omega sequences of ordinals are equivalent if they are we can get one from another by taking a finite shift or erasing an initial segment. Okay, but then we don't have choice. So this is a theorem of templates showing that if we take the iterated ultra-hard like that of the embedding, it is true that when we take the intersection, we are going to get a model of the form m omega extended by I'm writing it slightly imprecisely, but the sequence of equivalent classes of P alpha. But we don't have any choice function from those equivalent classes. So it's a model of ZF, it's not a model of choice. In some sense, it's also a model of failure of SH, but who knows what failure of SH means without choice. So let's try to restore choice. So we want to add a choice function, taking a representative from each equivalent class. Okay, so how are we going to do this? We are going to pick a generic. So let's take P star to be the first thing that essentially, well, it's the first thing in V that tries to guess what the initial segment of the previous sequence is. So it's a partial function, the size is mod kappa, from lambda to finite sequences of ordinals, increasing finite sequences of ordinals below kappa. The cone form. Okay. So each condition here, and it is again forcing over V, tries to give some information about the choice of the representative from F alpha. But you cannot get all the choices together without actually forcing things. And this is why, very asking why I changed the title of briefly forcing without forcing, because here I am forcing things. But I'm forcing a quite simple, I'm using a quite simple forcing motion, just the point well understood. Kappa plus is primitive forcing, which means that it does not add any sequences of ordinals of size kappa or less. Okay. So we want to think about this generic as trying to pick sort of randomly representative from each equivalent class. Okay, now we need to say a few words about lifting such an embedding, or lifting an elementary embedding like the extender-based one after we do a generic extension by subject-level concept. The relevant definition here is the definition of width. The width of an embedding is the least cardinal mu such that every element in the target model N is essentially representable by some function of domain U from N. Oh, I didn't write it F is in N. F should be in N. So there is some function F in N such that the domain of F is mu and F is in the range. And the embedding using the kappa lambda extender has width. This is the only package we need to know. This is the only place in which we actually use the combinatorial definition of the Tollnet embedding. And there is a lemma, I think, I'm not sure if it's due to Wood or maybe earlier than that, saying that kappa plus is primitive forcing when I'm adding a generic filter for coupled class distributed forcing for my model, elementary embedding linked in a unique way. There is a unique way to define a generic filter over the model N. This is the H field. It's the only way to do that. And there is a unique extension of J to J field, sending H to H field, extending it. If you think about this for a few minutes, it is really the only way to do it. So what do I want to get from this? So I'm saying if you take a generic filter over 3 for this coupled class distributive forcing, you can move it to the next model, to the MNs. But we don't quite want to just move it, we want to also change. This is a very delicate point. So we want to say the following. We start with our generic H. And then let's think about n equals 0. So what is H1? We start by pushing H through the first embedding J1. We get a well-defined generic filter for the image of P0, P star in M1. It's really already a generic filter, but now we want to modify it, and we modify it by changing the sequences that we can. So we take all the alpha that came from B, and we change the point J of alpha by adding alpha. It's the last point of this finite sequence. So we make the generic at those points slightly longer. Each condition P is going to be changed when we look at JP. JP is going to be changed at most couple many. So what we get is still a condition, still an element in M1. And moreover, the filter that we are getting is generic. And this is again not very difficult to see because from the point of view of each one of the MNs, we actually did right? A small modification to a generic filter. So again, MN cannot really apply this modification because MN does not know about the pointwise image of JNN plus 1. But for each condition separately, MN can apply this modification and can see that it is small. And now it's not very difficult to see that if you have a if you have a dense open set in MN, you can find a condition in any generic filter contains a condition in this dense open set such that every small modification of it will still be in this dense open. Okay, so it's not really static, even like you think so. Great. So what is going to be our generic? What is going to be our P alpha? So we're just going to look what is going to be accumulated in those in the coordinate alpha when we study the HN all the way through to momentum. And we see that once alpha is originated from some MN, the previous sequence is coordinated starting to grow each step by 1, and eventually this P alpha is going to be an omega sequence of ordinals below kappa omega. And they are going to be distinct from each other. For each alpha less than beta, P alpha is going to be strictly less than beta on a affine set of probability. Okay. Note that this procedure can be done inside each one of the MN HN. So if we are working in MN HN, we can actually apply the embedding and modify the generic as we did for and get n plus 1 h n plus 1 n plus 2 h n plus 2 and so forth. And eventually we're going to get m omega of g. So m omega of g is certainly contained in the intersection of the m and hn. Each one of the m and hn is a quite nice model. It's actually a model, it's a generic extension of mn in which we did not collapse carbon. Okay? So the same arguments as before, talking about continuity code, talking about not adding bounding sets, everything goes smoothly. The only thing which is a bit more difficult is the interpretation. I'm not going to say a lot about this, just saying that the start here means that I'm almost sure that the proof works, but it's not fully checked. So if you would ask me yesterday, I would say that it is probably true. Now I'm saying that it is almost surely true. But it's way more complicated than the Bukowski diagram. So what did we get? We got a model, m omega of g. This model satisfies that SH squared the kappa omega. Indeed, 2 to the kappa omega is going to be lambda. And lambda omega to the omega. And we got the GCH holds below kappa omega. Actually, m omega agrees with m omega g about the subset of kappa omega. Got a model to the standard basis. Question? What? Yeah. Not sure. But feel free to ask questions because otherwise I slightly okay. Okay, so let's see. So the last. Okay, so I'm going to rush a bit about this part, but I would like to give a hint how to get a forcing from this method. So we got a model, m omega of g. We know how to modify. In some sense, we said we start with a point forcing and we slightly modify at each point in order to eventually get a generic. And we can go in the other direction, like the original one, and get a forcing notion in this doing the same thing. Okay. So for this, okay, I'm going to say. So I would have to define what is an extender. So we are going to use the definition of Merimovich for an extender in which we are looking at all the measures are measuring essentially strictly increasing sequences of length less than kappa and kappa, and the generators are going to be increasing sequences of length at most kappa, leaving m or below general kappa or below lambda. This extender has a nice feature that the projection maps are really easy to describe, are simply the restrictions. Okay? So once we, and crucial, if we're taking the power using the extender, either portion, so if we take any elementary embedding, we can derive an extender, and there is a portion gap between the autopower using the extender and the original elementary embedding, which is the point about lambda. So it is going to catch tolerates, which is what we care about. The projection maps between the measures is simply the restriction when we need to think slightly about what happens when the d outside the kappa and yeah, and it is by the definition it is the kappa lambda So we have a sequence of measures indexed by when the index went by increasing sequences of length multiplied below the lambda. They have a nice feature of being reduced to each other, projected to each other by the restriction, and this is the combinatorial object holding our element in there. But the forcing is what. So as before, when we defined the forcing using an iteration, we talked about a tree. Right? We had a tree in which at each point we had a large set of extensions. Here we need one additional piece, which is the condition in the generic for the HNs. So it's going to look like F and T. F is a condition in the point piece. T is a tree which is large with respect to some measure. Which measure it can be? It has to be the domain of F. The domain of F, enumerated as an increasing sequence, is going to be exactly what we, the generator of the measure. The tree is a tree of finite elements, which each one of them is a sequence of less than half many ordinals on top. Okay, now, so essentially each one of the, maybe I should be more precise, each one of the n is essentially a partial function from a subset of the domain of F to K. And the extension is the natural one. We can extend the F, we can shrink the T, but we have to be careful because once we extend the F, we actually change the measure, so we need to project the tree to the right. And the projections is always the restriction, so things happen pretty naturally. Okay, how the non-direct extension works like? It actually should represent what we do when we move between Mn and Mn plus 1. So what did we do when we moved from Mn to Mn plus 1? We added the generators. We added this J image of alpha and something. So this is exactly what happens here. We're adding for each alpha such that alpha is in the domain of nu. We're adding to F alpha a single element which is neo alpha. Then we're shrinking the tree. We start the tree about this. It might look a bit weird now, but it's actually pretty straightforward translation from what we did in the iteration to the language of forcing. Everything that we did in the iteration translates to the piece of the definition here. Okay. And eventually the order of the forcing is just a transitive closure of those two possibilities, either taking a direct extension or taking a quick extension. And I feel with the remote, which is it is the right forcing. M omega of G, the model that we defined, is really a generic extension of M omega using this extended by expressive forcing as defined in M omega. Questions so far? Okay. So in the last 2 minutes, let me say a few words about collapse. What do we do if we want to actually add collapses? If we want to collapse, let's say that we want to make kappa to be alpha omega. Well, obviously we cannot do this inside V because kappa is very far from being alpha omega. There are many cardinals in between. We need to collapse them in order to make sense of it. So here's the clear version. Okay, let's say that you actually give me a generic for the collapse between, let's say, omega 1 and kappa, collapsing all the cardinals in the interval for K0. Then I can find over some iterated of V a generic G such that M omega of G satisfies that kappa omega is alpha omega and all other cardinals of the set. How do we do that? So, really in a sketchy way, we are going to pick a generic over M1 in V for the collapse. This is possible assuming, let's say, instance of a GCLH, K1, and we are going to push K1. We are going to push K1 through the index. So we apply the auto power embedding on K1, getting K2, which is generic over M2. We apply the next auto power embedding, getting K3 over M3. And now it's really easy to verify that those sequence of generic features are actually mutually generic. Simply follow from chain condition and closure arguments. And if we look at the whole sequence of features for each G, then we get that it is actually the M omega together with P and G is actually the intersection model of all the MNs with the finite product of the collapse. And the arguments here are very, very similar to what we had before. There is a slight additional trick in deriving the fact that it is actually the intersection, but at least the fact that it is concluded here, so the fact that the intersection of the MN together with the final product of collapse contains M omega with P and G, this is trivial, right? This is just the usual computability argument that we had always put. So it means that if you don't care about about the intersection being exactly M omega PG, but you just care about M omega PG computing the right cardinal in the right way, then you can do it in the very same arguments that you have so far using the continuity of J omega for cardinals above top omega and using the increasing critical points in order to deal with cardinals below kappa. Okay. Let me stop here because I started late from my.
Questions?
So in the last argument, you have to add the class to them, bring that over down to some
Yes,
the drawing, so you can
this one. Kappa 0.
oh I see, okay, thank you.
Making kappa in altitude.
Other questions?
Wait, can you go to the next slide? So do you get K1 from K0?
No. K1 is something that I'm getting in V. I construct it inside V. It's going to be mutually generic with respect to K0 over M1 because K0 is generic over V. But it is constructed independently.
More questions? Oh, then let's thank you.